Hello. Now, in this topic, I will talk about the topic diffraction. See, if I take a situation, there is a person here is standing behind this wall, another person is standing on the other side of the wall. If this person speaks, this person can hear the sound, but this person cannot see him, and vice versa. If I am speaking here, my voice can be heard in the other room, in the next room, but I cannot be seen. So what might be happening here? That sound waves as well as light waves, they move here, and maybe sound waves bend and they are able to reach, but light waves can't bend like this. Sound waves can. This bending of light or sound, or rather bending of waves from the corners of obstacle or aperture is called diffraction. Here I have taken obstacle, let's take an aperture too. Aperture means a narrow opening. If I put a screen here, this is an aperture and there is a source S. So what do we expect? Light and everywhere in between these 2 points, light will be going. So here we expect bright, we expect light, and here we expect darkness. Light travels in a straight line, but try to observe any shadow. It is never too sharply defined, and here also it will never be that up to this we have light and then beyond this point there is complete darkness. This comes gradually actually. Some light enters into the shadow region also. This is called a shadow region. Same way the light enters into this region also. This is the bending of light when it is passing through the aperture. So some light always enters into the shadow region. And how much will be the bending? That depends on the size of the obstacle or the aperture. So diffraction is bending of waves from the corners of the obstacle or the aperture. That is called diffraction. And to observe diffraction, two conditions necessary. First, size of the obstacle, that's most important. Size of the obstacle must be of the order of wavelength of waves. Wavelength of the waves. In case of light, the wavelength is very, very small. So we need very narrow apertures or smaller obstacle to observe this diffraction. While in case of sound, the wavelength is very large, so even we can observe it with bigger obstacles or bigger aperture. That's why we observe it in daily life, but for light it's not too common. For light, another thing to observe, we will see that we get maximas and minimas and all that. For that it's necessary that we should have monochromatic source of light to see sharply defined maximas and minimas. Otherwise, bending, narrower is the aperture, more is the bending. Now let's talk specifically about bending using a narrow slit, single slit. I am taking a source of light, monochromatic source of light. See, if we take a polychromatic source, then each wavelength will produce its own diffraction pattern. And first let me explain what do I mean when I am saying diffraction pattern. If I keep S at the focus, the light rays will be parallel. The purpose of taking this is so that I deal with plane wavefront. If I take a point source, there will be spherical wavefront. Diffraction will be observed in both the cases. Okay. And this is the screen. So we have a light source let lambda be the wavelength, let d be the width of the slit, and we want to observe what is happening here on the screen. This should be narrow. Now I am showing you an activity. I have taken a slit which can be made very easily. I have used blade. You can take a normal blade, and sharp edges must be kept very close. You can take a piece of cardboard, make a hole, and then put the two parts of the blade here and then pass light through it. Monochromatic means laser torch is the best source available. So you can use a laser torch. Wavelength is 1. When you pass through this, we get a pattern with a lot of maximas and minimas. Just observe the activity that I am showing, and then we will come back to it. On blade we can make a single slit like this. In labs you can find the single slits of variable width. We can vary the width of this slit using this screw, and that we get as a result of diffraction from single slit. If I increase the slit width, then this pattern changes. This is when I am increasing the slit width. And this is when I am decreasing the slit width. Okay, what have we observed in this activity? If I plot intensity graph, we have a maximum intensity. Actually, there is a maxima at the center, which we name as central maxima, and then there are lot of maximas after it. Maxima, minima. Other maximas we call them central maxima. So central one, central maxima, and then secondary maxima. Central maxima, secondary maxima. Similarly on the other way. First secondary, second secondary, and third, all those are secondary. So this is the central maxima or primary, and then we have a lot of secondary maximas of decreasing intensity. This is how it differs from the interference pattern. This is what we call as diffraction pattern. So we have maximum intensity at the center, and then we have a number of maximas with decreasing intensity, and then we enter into the geometrical shadow region where we have no light. So between that shadow and the center, we have a number of maximas. This is diffraction pattern. I can write the values of lambda, the part difference, that we will come to it later. First, just see that the intensity is maxima at the center, and then it gradually decreases. Now, why do we observe it? What is the reason for getting such pattern? See here. Now light, if I take a point O, let us name these 2 points, extreme points on the slit, as A and B. So if I see at O, I have to, now we have just one source of light. We don't have two sources, single source, plane wavefront. Now Huygens principle says that every point on this primary wavefront will give secondary wavelets. So now from every point, from this point, from this point, and from this point, from this point, every point between A and B a large number of points we can assume, all of them producing the secondary wavelets, and then they interfere and giving us the pattern that we have shown. So diffraction pattern is the result of superposition between the secondary wavelets coming from the same wavefront. It is unlike in interference. Interference, we have two coherent sources and there is superposition between the two waves and we get maximas, minimas. But here it is the interference between the secondary wavelets of the same wavefront. That is the cause. At O, if I take a secondary wavelet from A, secondary wavelet from B, they are covering the same distance, and similarly every one. If I divide it into two parts, say AC, CB. So every secondary wavelet in the upper half has a corresponding wavelet in the lower half with 0 part difference. So at O we will have maxima. Let me take a general point now, P, and let us take I am taking those secondary wavelets which are reaching at P. From here, this theta will be called the angle of diffraction. Okay. Now, I want to find out what will be the intensity at P. If I take two extreme points of the slit, A and B, then this one, let us name it M. So BM, this is the extra path that this secondary wavelets covers in reaching P. So actually the path difference between A and B is BM. This is the path difference between secondary wavelets going from A and B. After this, they have covered the same length of path, right? This is the extra path covered by B. So the path difference between the secondary wavelet from A and from B when they reach P is Bm. And what is the value of Bm? This is theta, this is 90 minus theta, so this is theta, this is hypotenuse. I need the perpendicular. This by this is equal to sine theta. So actually this becomes d sine theta. This is theta, 90 minus theta, theta. From this triangle, this is d, this is what I want, and this is sine theta. So sine theta is perpendicular upon hypotenuse, so Bm becomes d sine theta. So d sine theta. Now let us take a situation when d sine theta is lambda. That is, the secondary wavelet from A and from B have a path difference of lambda. Now let us take this slit as if it is made up of two parts, AC and CB. AC and CB. Now, if the path difference between the secondary wavelet from A and B is lambda, then the path difference between the secondary wavelet from A and C will be lambda by 2. Or I can name 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 20. Let us assume there are 20 secondary wavelets moving out. So, 1 and 11, they have a path difference of lambda by 2. Similarly, 2 and 12 have part difference of lambda by 2. 3 and 13 have part difference lambda by 2. What I want to say is, every secondary wavelet in the upper half has a corresponding secondary wavelet in the lower half such that the path difference is lambda by 2. And what is the meaning when we say path difference lambda by 2? Phase difference of pi, and this gives us minima. So this will give us a minima at P. Understand? Again, if this is lambda, the path difference between the secondary wavelets from here, I have divided this slit into two parts, AC and CB, and I told you that if the path difference between these two secondary wavelets in reaching P is lambda, then path difference between this and this will be lambda by 2. Same way, I am coming down from here and the same distance from here, again they will have a path difference of lambda by 2. So thus there will be a minima. And same way, I can do it for 2 lambda, for 3 lambda, for 4 lambda. If the distance is 2 lambda, I will take the slit as made up of 4 parts. Upper 2 will behave exactly in the same way lower 2 will behave. So d sine theta lambda, 2 lambda, 3 lambda, this will give me a minima. So d sine theta n lambda, this is a condition to get minima. Now let me take, if d sine theta is 3 lambda by 2. I am not taking lambda by 2. Why? Try to understand it. We got central maxima at 0 and we got first minima at lambda. 0 maxima and at lambda we have the first minima. So the next maxima will be after lambda only. So I am taking 3 lambda by 2 directly, not lambda by 2 that is covered in the central maxima. Okay, now let me take this slit made up of, say, 3 parts of equal width, AC, CS, and again let me take 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, this, and then 21 to 30. 10 parts this, 10 this, 10 this. This is just an assumption. I am taking a number of secondary wavelets are there. I am assuming that there are 10. Now, if the part difference between this and this is lambda by 2, then the part difference between 1 and 11 will be lambda by 2, lambda by 2, lambda by 2, lambda by 2. This will make it 3 lambda by 2. Same way, right? 1 and lambda will be 3 by 2, 1 and 11. Same way, 2 and 12, lambda by 2. So it means every secondary wavelet in the upper half, this part, upper 1/3 part, has a corresponding wavelet in this part with a part difference of lambda by 2. So this will cancel out. But still we are left with 1/3 part. So this 1/3 will produce some intensity at P. But obviously, if 2/3 part is blocked now, so we are getting intensity only due to 1/3 part. So there will be a maxima. And same way, it will be a maxima for 5 lambda by 2, for 7 lambda by 2, and so on. So d sine theta this is a condition to get secondary maximas. Minima and secondary maxima. So now we can plot the graph that I had drawn initially. And let us take, we can plot it versus path difference, we can plot it versus the angle of diffraction. So d sine theta n lambda. This is the condition for minima. So for small angles, I can write like this, and theta is n lambda by d. So this will give me the conditions for minimas. So I can find out the position of different maxima. So angle of diffraction, first minima is coming at lambda by d. Second is 2 lambda by d. Then third is 3 lambda by d. And same way here, lambda by t, 2 lambda by d, and 3 lambda by d. So this is how it has been drawn, intensity versus theta, the angle of diffraction. Okay, now what is the width of the central maxima? And then other maximas too. We can find out the linear width. Just try to recall the pattern that I have shown you. There was maximum intensity here, and then minimum, and then we have another maximum, and then another maximum, and same way. These were secondary maximas, primary maxima, or central maxima followed by number. I want to find out this. This will be the linear width. And if I find out this angle, that will be the angular width. This gives me the position of central maxima. If I plot like this, okay, this is the angular width of central maxima, and this angle we got lambda by d. So this total becomes 2 lambda by d, angular width of central maxima. This is 2 lambda by d. What will be the linear width? This distance is d. Angle is equal to arc upon radius. Arc, this is the width upon radius. So width will be d into, so d 2d lambda by d. Linear width of central maxima. I want to find out this only. So angular width we will get from it. First minima here. So I can find this angle using this. This is lambda by d, this is lambda by d, 2 lambda by d, and divided by this distance, this will give me this. Angle is equal to arc upon radius. So this is, and fortunately we are getting the same expression. D lambda by d was the fringe width. It is just double of that. And we see that all these, if I find out the difference of these, then for secondary maxima, you can find out second 2 lambda by d, third 3 lambda by d. What is the difference between them? Just lambda by d. So in that case, the width of secondary maximas will be only this much. This is half of that. So central maxima has double width to that of other secondary maximas. Now another point in diffraction that needs to be covered here. If we have a light beam of width A then we have seen that this is the spread. So whenever a light beam of width A is passing through an obstacle of width A, there is a spread of lambda by A. Right? Lambda by A. In rectilinear propagation of light or ray optics, we have done that the light travels in a straight line. But here we see that we are saying that light bends when it passes through an obstacle or aperture. And now, depending on if this is a screen, depending on this distance, this linear spread, the linear width will also change because angle is increasing. So if angle is increasing, this spread on the wall will keep on increasing if we take it back. So just find out that how much will be for this angular width. Again, we can find out if this distance is d. Angle is arc by radius. Angle is, use this if we have to find out this width. So x by d is lambda by a, or x is d lambda by a. This will be the width of the beam. A light beam which has a width a passing through an aperture of width a, after passing through it, it will spread, the width will increase because of diffraction, and on a screen placed at distance d, this width will become d lambda by a. Now, rectilinear propagation of light means light travels in a straight line. So ray optics and wave optics, I want to tell you the condition when we can ignore the diffraction, and the condition was set by Fresnel. Fresnel distance is that distance up to which this spread is equal to this. So if d lambda by a is equal to a, this spread equals to a, then this is called Fresnel distance. So Fresnel distance is the distance, that distance up to which the spread of the light beam equals the width of the slit. If the distance is more than this, then that approximation that light travels in a straight line actually breaks. So we can use that approximation of light traveling in a straight line up to a distance which we have defined as Fresnel distance, a square by lambda. So that's all in this topic. Now next we shall take polarization of light.